Hello everyone, my name is Eduardo Martins and this is my video lab report for Lab 5 for Physics 2211. In this lab, we're going to explore the effects and consequences of using the iterative approach to simulate physical models. I'm going to use the harmonic motion in this experiment because it's very easy to implement in an accurate way. The harmonic motion is going to be caused by the force of a spring, which is proportional to the displacement of the object in relation to the center of the spring. And we can check that if the displacement of the object is given by this equation, then we do end up with the force or the acceleration being proportional to minus a constant times the displacement. This omega in these equations is the angular speed of the system, and at each given point of time t represents the stage at which the oscillation is. So here we can see how we obtain it. And in this experiment, we're gonna use the initial velocity 0 because it's much easier to find all the values we need to simulate the system. So this is how the calculations play out for us to find phi and a. We then conclude that for a starting velocity of 0, the object must be in either extreme of the motion. We're going to determine which one it is with the initial position. So it's kind of the same process. So since by convention A, the amplitude of the motion is always positive, we have this relation which tells us that if x0 is positive, then phi is 0. So this is what we're going to use in the simulation because it makes everything easier. Now, obviously the system here is composed only by the mass that's moving and the spring. And in the iterative approach, we're going to use, besides Hooke's law, which we've used here, the Newton's second law, which is familiar to everyone, I hope. So here's my code for this lab. Um, we're setting both balls to be like equivalent, and we're gonna start with delta t of 0.1 seconds just to see how it plays out. Here I'm just choosing arbitrarily a um, relaxed length and a spring constant, and here I'm setting up everything we need for the simulation. Here I update the position of the ball with the accurate model, which is precisely what the motion should be. And here I update the position for the iterative model. We can see that there are much more steps here, but we're gonna talk about that later. Um, so I'm gonna run this program now, and we can see that there's a considerable difference between both models. So what we can do to make this better is to decrease delta t. So we're gonna make it 10 times smaller now, and we're gonna see that the precision of the simulation gets much better. See, it's basically the same thing now. So now what we're gonna do is the exact same process, but for many different delta t's from 0 to 1 seconds, and we're gonna add up all the squares of the differences of the positions of both balls at each time step, and see, and this way we can see um, how bad the iterative approach is compared to the actual one, depending on the delta t. So this is what we get. We can see that as the delta t increases, the sum of the square error gets bigger, but at some point it gets like exponentially big, and we can see that with for bigger and bigger delta t's, the simulation is just crap. But what does that mean? That means that for a smaller and smaller value of delta t, the simulation approaches what will happen for an infinitesimal time step, which is exactly what the accurate model represents. So, for example, what if instead of this simple situation, we wanted to use a v of 0 that was not 0, or we wanted to have multiple springs connecting to the ball, or much more complex situations? We could find the actual precise model, but that would be much, much harder than just setting up the forces and an iterative approach with a very small delta t. So we can conclude that although the iterative approach is not 100% precise, it is definitely worth trying if the simulation you're doing is not um, required to be 100% precise, but instead it could be like 99.9% precise with a small enough delta t. Thank you.